David Kazembe, and my project was on the design of a wastewater treatment plant for water reuse in beverage manufacturing industries. Oh, okay. So I can start again. Okay, so my name is David Kazembe, and my project was on the design of a wastewater treatment plant for water reuse in beverage manufacturing companies. So the motivation behind this was that a lot of beverage manufacturing companies generate a lot of wastewater, mostly from bottling, cooling, and cleaning processes in the production line. So there's a lot of potential to clean this water and reuse it back in the production line. So you find that in this wastewater you have a lot of organic matter, sugars, BOD levels. So if you're able to treat this water, you can reuse it back in the production line, and industries can save a lot of cost, water bills can be reduced, and at the same time, you also be reducing the environmental impact on the society. So the main objective was to design this wastewater treatment plant, and it had 4 specific objectives. The first objective was to quantify the amount of water that is generated by the beverage manufacturing company. For this case, it was Chibuku Products Limited. So when calculating the amount of water that was discharged from the factory, we had to go through the water bills to find how much water is generated per day. And then after that, we use that to inform our design. So you see that I have the prototype here, and within the prototype, we have different sections. The first section is the sedimentation tanks. So we used the amount that we found from the analysis, which was 85% of the water that is used in the beverage factory is regarded as wastewater. And from this represents the sedimentation tanks. The sedimentation tanks basically just allows the water to settle. It allows the water to settle so that it can go to the next section, which is the filtration tank. The filtration unit, what it does is it absorbs some of the sediments in the wastewater. For example, in this case, Chibuku, it has a lot of grains, sediments. So as the water is going through the filtration tanks, in this case, we used aggregate stones. So for the aggregate stones, we used between 20 to 2 meters in aggregate size. The first container has aggregate size containing 20 millimeters. So once the water passes in there, a lot of the sediments are trapped, and as it goes to the next sedimentation, the next filtration unit, the same happens. The final one is the sand filtration, which further absorbs some of the sediments that have been found in the wastewater. So for this one, after that was done, after we passed the wastewater through the prototype, we had to analyze the water that comes out at the end. So when analyzing the water, there are several parameters that we had to check. The first parameter was the electrical conductivity, total dissolved solids, pH, the turbidity, total coliforms, and fecal coliforms. Our main interest was the fecal coliforms because these are disease-causing organisms. So if people, for example, in the beverage factory, they are using this water for cleaning, we want to make sure that there are less fecal coliforms to avoid people contracting diseases. So our target was to make sure that we reduce the fecal coliforms to at least less than 50. And we just hit the target on the nail, but we were not able to go less than 50 for a number of reasons. But you can see that in terms of the other parameters, the pH, the total dissolved solids, and the electrical conductivity, the efficiency was 50%, meaning that our treatment unit was working efficiently. And at the same time, this shows the design of the sedimentation tanks. For the design of the sedimentation tanks, there are several criteria that we had to use. That was the volume, the amount of flow rate that we had to come up with the dimensions. And this shows the treatment unit working. We are cleaning the Chibuku water, and here it's coming out of it. And for the recommendations, for this one, we're using the filtration media. So for filtration media, we're using aggregate to trap the sediments. But then I would recommend that to optimize this system, we incorporate an aeration system. An aeration system allows air to go into the filtration units so that more air comes in and we make use of the respiration so that microorganisms can feed on more organics that are present in the wastewater. As such, as the microorganisms are feeding, on these organics, we reduce the amount of contaminants in the water. So to further enhance this system, we need to include that aspect of aeration, and maybe we can add an aerator. The only issue is that most of the aerators are expensive. So a cost-effective aerator that can be incorporated into the filtration unit to further enhance the efficiency removal of the contaminants. In terms of challenges, for the BOD, you can see that the efficiency was only 15%. And the challenge comes in, as I said, is that we didn't use an aerator, and the only reason we don't do that is because of the cost issues. Because of an aerator, we have to incorporate air in the system to allow more microorganisms to feed on these contaminants. It will further reduce our BOD levels in the water, in the wastewater system. Okay, so BOD is the biological or chemical oxygen demand. So it's the amount of oxygen that microorganisms need in order to digest organics in a wastewater sample. So it's just the amount of oxygen that the microorganisms will need to digest any organics in the wastewater. So in terms of scaling up, essentially it's incorporating the aerator. The aerator is like a propeller. It propels one of the tanks. It allows air coming in. So as the air is coming in, microorganisms have more oxygen to digest any organics that are in the wastewater. So as such, as the organics are being digested, you have a lot of contaminants being removed. So that aspect of aeration comes in with a pump, so you need energy as well. So as I said at the first, we are trying to reduce cost for the beverage manufacturing companies. So if we come in with another energy equipment, costs are going up. So we just need something that is cost effective, maybe we can use solar energy, any renewable source of energy to power the aerator. Cashing in, yes. These are systems, for example, in Malawi, only Coca-Cola beverages in Europe uses a wastewater treatment plant, and they don't reuse the water. They discard it to the municipals. So there's an opportunity for them to reuse the water. And a lot of beverage manufacturing companies don't have that aspect where they use the water and reuse it. So the customers represent the solution. Because a lot of these companies, they use a lot of water. You see that per liter of beverage, most of them will use about 3.5 liters of water just to produce 1 liter of Coca-Cola, for example. So if we narrow down the amount of water usage to, like, let's say for a liter, you produce 1.2 liters just on a liter of beverage, that would be better. Because that way, they're saving the cost and they can put that money elsewhere. So as the wastewater is generated from the factory of the brewery, it enters this sedimentation tank. So it will enter this sedimentation tank. As this sedimentation tank is full, we'll open this valve after a certain period. Let's say detention time of 1 hour. As we detain this water, we'll open the valve. Once we open the valve, the water will enter the filtration unit. In this filtration unit, water will pass through the aggregates. In the aggregates, some of the sediments are absorbed by the aggregate particles. And the same goes as it moves to this filtration unit. So this one has 20 mm aggregate size, and this one has 10 mm aggregate size. So as it enters in here, the same filtration happens, just further filtrating the water that is coming from this tank. Finally, as the water comes from this filtration tank, it will enter the last tank, which has sand filters. The sand filtration also further treats the water by removing sediments that were not able to be removed in this tank. From there, then the water can go into the tanks for storage.